So hi friends, my name is Chen Hao and today I will be explaining to you the difference between centripetal force and centrifugal force. So the two forces, centripetal and centrifugal, might often be confused with one another because of their similar properties. But in this video, I will explain exactly what is different about them, and hopefully by the end of the video, you have a clearer idea of the differences and similarities between centripetal and centrifugal forces. So you might have seen the following statements about centripetal force and centrifugal force in your textbooks. So firstly, centripetal force is it keeps an object in circular motion. Secondly, centrifugal force is an inertial or a fictitious force. Thirdly, centrifugal force has the same magnitude but opposite direction as the centripetal force. Number 4, the object in circular motion moves at constant speed. Number 5, the object in circular motion has a constantly changing velocity. So number 4 and 5 might seem to be contradictory, but they are in fact consistent with one another because speed and velocity are different things. Speed is a scalar, whereas velocity is a vector. So velocity has both magnitude and direction, whereas speed only has a magnitude, and it's the magnitude of the velocity. So let's first understand what it means to have an object in circular motion. So let's say we have a point in space and there's an object that goes around this point in space in a circular fashion. So this object, denoted by the circle here, at time t equals to 0, it's here. Then at time t equals to 1, it's here. At time t equals to 2, it's here. T equals to 3, t equals to 4, and so on, and it goes in a circle. So when this object is now following the path of a circle around a point. Now let's understand what the velocity of this object is. So we know that the velocity is the change in position with respect to the change in time, is the derivative of position, right? So if we denote the velocity with red over here, you can see at time t equals to 0, the velocity is the red arrow over here, is the red vector. So this is the velocity at time t equals to 0. And this velocity is perpendicular, is tangential to the circle, is perpendicular to the radius. And then at time t equals to 1, the velocity is now tangential to the circle at the point where the object is at t equals to 1. So it is also tangential. So this is v at t equals to 1. And at time t equals to 2, the velocity is here. At time t equals to 3 is also tangential. At time t equals to 4 is also tangential. So that is, the red arrows denote the velocities of the object at different times. So you can see that the red arrow, the velocity at time t equals to 0 is pointing up. Then at time t equals to 1 is slightly slanted, right? And this velocity has, in a sense, rotated. And that means that it's no longer the same velocity. That is why we say that the velocity is constantly changing, because velocity accounts for both magnitude and direction. Whereas, if you compare the lengths of these arrows, you'll find that the lengths of these velocities, the magnitude of the velocities are constant, and that is why there's constant speed. So we have covered property 4 and property 5 in that we now understand that the object in circular motion has a changing velocity because the velocity arrows are changing direction, but their magnitude remains the same. So throughout the circular motion, the object has constant speed. So with property 4 and 5, we now investigate what happens to velocity. So in order to have changing velocity, we have established and understood that when an object undergoes circular motion, it must have a changing velocity. And this changing velocity means that acceleration is non-zero, because acceleration is the change in velocity over the change in time, right? So because the change in velocity is non-zero, A, must be non-zero. There must be some acceleration that is experienced by the object. Now, because according to Newton's second law, F equals to ma, then we now deduce that there must be some net force acting on the object in order for its velocity to change. And this is known as the centripetal force. Centripetal force. So let's draw another diagram here to illustrate what the centripetal force does. So let's say with the center of rotation here again, and some distance away we have the object. The object is currently traveling at velocity v, and the centripetal force acts on the object towards the center of the circle, and this is force F. This force F would then cause, according to Newton's second law, this force F would cause an acceleration and a change in velocity of the object, denoted by delta V in yellow. Then if we add the current velocity and the change in velocity, we get a resultant velocity that is denoted in orange, V prime. So we can see in summary that in order to go in a circular motion, in order to maintain the circular motion, the object must undergo changing velocity. So in order to have changing velocity, there must be some force that acts on the object. Because if there's no force, then the object will just have constant velocity and go in a straight line. So in order to change the velocity of the object, there must be some force. There must be some force, some net force acting on the object. And this force is the centripetal force. So that is what the centripetal force is. The centripetal force is the force that changes the velocity of the object such that the object can maintain its circular motion. So we have then covered property number 1. And you can see this more clearly. We can see this more clearly if we cut off that force. So if, let's say, while the object is traveling, I suddenly cut off this centripetal force. Then there will be no change in velocity, and there'll be no, and the resultant velocity would just be the red arrow over here, and the object would then travel in a straight line and hence not maintain its path of circular motion. So without the centripetal force, the object just travels in a straight line. So the centripetal force is the force that keeps the object in a circular motion. So now that we've covered centripetal force, let's go through a few examples of what centripetal forces are. So centripetal force must come from somewhere, right? Because the force must come from somewhere. So this force, the force's origin differs based on the example. So in the case where you have a rope, you're holding onto a rope, and the rope is attached to a ball, and the ball is going in a circle, the centripetal force in this case is the tension. So the tension in the string acts as the centripetal force holding the ball within its circular motion. Now for the case of planetary orbit, where you have the sun and you have Earth, the centripetal force that keeps this Earth within its circular motion is the gravitational force. So this gravitational force is the centripetal force that keeps the Earth in its circular orbit. Well, actually the Earth is not in a fully circular orbit, but that's beside the point. Now lastly, in the case of those Chinese dining tables, where you have this rotating table that brings around the plates of food, right? So there's plates of food. So this is also some sort of circular motion, and the centripetal force that keeps the plate within the uniform circular motion and not sliding off the table, the centripetal force in that case is the frictional force between the plate and the sliding and the rotating table. So these are three examples of centripetal forces, and in each case the centripetal force is different. So what I'm trying to say is that the centripetal force doesn't come from nowhere. The centripetal force must come from somewhere to keep the object in a circular motion. So if the centripetal force was not there, then the object would not be in circular motion anymore. And so the centripetal force, in summary, the centripetal force is the force that keeps the object in circular motion. So now that we have understood centripetal force, let's understand the concept of centrifugal force. Now I'll begin this explanation with an anecdote. So you might have experienced before when you're sitting on a merry-go-round or a carousel that when you're spinning, you feel like there's some force that's pushing you away from the center of the carousel, right? So this is actually known as the centrifugal force. Now straight away you can see that the centrifugal force is different. The centrifugal force is pointing away from the center, whereas previously the centripetal force was pointing towards the center of rotation. So that is clearly a difference between centrifugal force and centripetal force. So now back to the story, you're on a carousel, and when the carousel is rotating, you feel there's some mysterious force that pushes you away from the center of rotation. Now the natural question is then to ask, where does this force come from? So let's ask the question, where does this force, where does the centrifugal force come from? And the answer is, it is a result of you being in a non-inertial reference frame. Now there are some complicated terms here. Firstly, there's non-inertial, and secondly, there's reference frame. So what are these two things? So let me introduce to you the idea of reference frame. So I made a quick animation explaining what reference frame is. So first of all, you might imagine that if the reference frame is all about perspective. So if you are looking at an object undergoing circular motion, this is what you might see. And currently you're in a rest frame. You are sort of an observer looking from above, and you're seeing the object move around in a circle. However, if you look from the perspective of the object itself, you are now in another frame of reference. So now, if your eyes are centered at the object's location and you are following the object around the circle, then from this perspective, from this reference frame, you will see the world moving instead of the object moving. So once again, let me highlight the differences. In the rest frame, you see the object moving, and you're currently fixed in space. Whereas, if you are in the moving reference frame, if you're in the reference frame of the object in circular motion, you will see the world rotating, and you'll see the object staying still. So this is the whole concept of reference frame. And yeah, so this is the concept of reference frame. It's all about perspective. So the reference frame is a fancy word for what perspective you're looking at the world from. Now onto inertial. What is inertial? So if we take a look at Wikipedia, an inertial reference frame is a reference frame that is moving at constant velocity. So a non-inertial reference frame, so let me just write it down to be clearer. Inertial means constant velocity. And that means that non-inertial, so constant velocity means acceleration equals to 0. Whereas non-inertial means acceleration is not 0, so changing velocity. So a non-inertial reference frame, we put it together, is a reference frame, a perspective that you look at the world from, that the reference frame itself is changing in velocity. So this let me illustrate this example with a bus. So when a bus jams brake, let's say a bus is traveling at constant velocity and then it suddenly comes to a stop. Now for a brief moment, when you're in the bus, when it jams brake, you are in a non-inertial reference frame and you feel this force that pushes you towards the forward of the bus, and that is a result of you being in a non-inertial reference frame. And that is a similar mechanism occurring with centrifugal force. So in the bus itself, when you get flung forward, when you get flung to the head of the bus, when you get flung forward when the bus jams brake, there's nobody pushing you there's nobody exerting a force on you, but rather the force that you feel, the apparent force that you feel towards the front of the bus is a result of the bus changing its velocity. And the same mechanism goes for the centrifugal force. So let's take a look at Newton's equation over here. So let me first, so you might be wondering now, how does being in a non-inertial reference frame cause me to feel the centrifugal force? Now the answer is over here in Wikipedia. You can see that Newton's law of motion, Newton's second law to be specific, is only valid in an inertial reference frame, inertial frame of reference. So that means that when you are in a non-inertial reference frame denoted by RF, Newton's second law doesn't apply. It breaks down. Oops. In other words, F equals to ma is incorrect. Now this might be shocking, but do note that this is only in the case of non-inertial reference frames. So let me just recap what we have over here. So previously we have established that an object undergoing circular motion has a constantly changing velocity, right? And that means that if you're looking at the world from the perspective of the object, you are now in a reference frame. You are now in a reference frame that has changing velocity. And that a reference frame that has a changing velocity is a non-inertial reference frame. And in a non-inertial reference frame, Newton's second law doesn't apply. It sort of breaks down. And now I'll now link this to how you feel the centrifugal force. So of course, Newton's law breaking down isn't very helpful because it just tells us that Newton's law doesn't apply. How exactly does it result in the centrifugal force? Now here's where some of the maths comes in, and don't worry, I won't go through the steps, but what you can show is that besides all the forces F that act on an object, you need to add an additional centrifugal force in order for Newton's law to apply. So this is the new correct form of Newton's second law with this correction term over here. So in other words, because we are in a non-inertial reference frame, we need to modify Newton's second law. And how can we modify it? We can modify it by adding this additional centrifugal force term. And now you might seem to be thinking, wait, this doesn't make sense. Where does the centrifugal force come from, right? And you're right to think so. Where does centrifugal force come from? There's no agent that has applied this centrifugal force on you, unlike the centripetal force case. And the answer to that question of where the centrifugal force comes in is a result of the non-inertial reference frame. So, in other words, in a non-inertial reference frame of in other words, when you're undergoing uniform circular motion, when you're in the perspective of the object undergoing uniform circular motion, you are in a non-inertial reference frame, and as a result, the original Newton's second law doesn't apply. But instead, you need to add this additional centrifugal force term. And so the centrifugal force term is a natural consequence of you having a changing velocity. Does that make sense? So it turns out that this centrifugal force term has the same magnitude but opposite direction as the centripetal force. So when the centripetal force is pointing towards the center of rotation, the centrifugal force, this is the centripetal force, the centrifugal force that you need to add on is the magnitude, has the same magnitude but opposite direction. And this is not related to Newton's, so this additional centrifugal force term is a term that you need to add to modify Newton's second law in order for the Newton's second law to apply in a non-inertial reference frame. So once again, I hope that this is really clear to you. So let me just recap what I've said so far. So now we understand that centrifugal force is an inertial or fictitious force. It's not a real force acting on you by some agent. It's a force that is a result of you being in a non-inertial reference frame. So, and we have also covered number 3, that the centrifugal force has the same magnitude but opposite direction as the centripetal force. So in summary, now I'll go over what we have gone through for centripetal and centrifugal force. So for centripetal force, we first saw that in order for an object to undergo uniform circular motion, there must be some force that changes its velocity, because in uniform circular motion, the velocity is constantly changing. So there must be some force that causes this velocity to change, and that is known as a centripetal force. So this centripetal force is responsible for keeping the object in a circular motion. Without this centripetal force, the object would just travel in a straight line. So that is centripetal force. And then we saw some examples of centripetal force in physical systems. In the case of a ball on a string, it's the tension in the string that keeps the ball within motion. If you cut the string, you're losing all this tension in the string, and hence the object just flies off. If you cut away gravity, then the earth would just go away from the sun and not maintain its uniform circular motion. And then that's for centripetal force. And then for centrifugal force, what I've explained is that the centrifugal force arises when you are in the reference frame, when you are in the perspective of an object undergoing circular motion. So if it helps, I'm going to bring up this animation again. When you are in the reference frame of an object undergoing circular motion, you'll see the world spinning around you, and that means that you are in a non-inertial reference frame, because this object that you are looking at a world from the perspective of, you are undergoing changing velocity. Your velocity is changing, so your reference frame is non-inertial. And what we saw was that Newton's second law does not apply in a non-inertial reference frame. And in order to get the right physics, we need to modify Newton's second law by adding this additional centrifugal force term. And this can be derived, and the derivation is in Wikipedia, but I just want to hit right at the core concepts of what centrifugal force is. So the centrifugal force is a result of, in a sense, the centrifugal force is a result of the failure of Newton's second law in a non-inertial reference frame. So you can clearly see that centrifugal force and centripetal force are very different things. Yeah, so I hope that this video has been clear. And let me just mention one last thing, that the centrifugal force, once again, there's no agent that applies the centrifugal force on you. The cart in the carousel is not applying the centrifugal force on you. In a sense, your presence in a non-inertial reference frame naturally results in some fictitious force that appears, and that is known as a centrifugal force. Similar to how when a bus brakes, there's no agent that applies a force on you, pushing you towards the front of the bus, but it's the result of the bus undergoing changing velocity that pushes you to the front of the bus. So I hope that this link is clear. If you have any questions, please feel free to leave it in the comment section below. And yeah, I will leave my email in the comment section below if you want to discuss as well. So I hope that the difference between centripetal force and centrifugal force is now clearly explained and yeah, very apparent. So thank you very much, and if you enjoyed this video, please leave a like and subscribe. Have a nice day.